Okay, so last time we left off with alpha thalassemia, and today we're going to continue with beta thalassemia and concluding our section of microcytic hypochromic anemias. And this is like one of the most important anemias, so we have to study it properly. Now, at alpha thalassemias, we did understand that it was due to the gene deletion, but there is some difference in beta thalassemia's case, which is due to the point mutation. So you need to keep this in mind that the most important point, the most important differentiating point is that beta thalassemia occurs due to point mutations, and alpha thalassemia occurs due to deletion. This is something that must keep in mind. So if I were to highlight this, so this is something that you need to keep in mind, right? Now, where does the point mutation occur? It occurs in the splice sites. So you must know what DNA splicing is. It's basically what happens is that there is transcription, and then there is translation, right? So in between these two processes, this is translation. This is not transcription. So let's do it again. So there is transcription, and then there is translation. So between these two steps, there is RNA processing. What happens is that before the RNA is translated into a working protein, uh, it is supposed to undergo some processing. So, if this is a DNA sequence, it has multiple sequences that are either active or they are inactive. So, introns and exons. If this is an intron and this is an exon, right? So, what happens is that because introns are inactive, so splicing cuts off the inactive parts, right? This is also an intron. So it cuts off the inactive part and only leaves the active part in the gene, so that this RNA this RNA molecule can get translated into a certain protein. So what they do is what happens is that there is point mutation in the splice sites on the Kozak consensus sequence on chromosome 11. So chromosome 11 is quite important. Something you need to keep in mind is quite important, right? Now, what Kozak consensus sequences is that uh, it's just a promoter sequence. Now, there is a bit of a contradiction here. Is that they have mentioned Kozak consensus sequence as a promoter, right? They mentioned it as a promoter, but however, there's a difference between both of them. A promoter is just a DNA sequence which is upstream of a gene where RNA polymerase binds to initiate transcription. So, for example, if this is a DNA sequence, right? So there's going to be if this is a gene, that's it, for example. So if this is a complete chromosome gene, right? So there's going to be a DNA sequence somewhere where the RNA polymerase is going to bind and start the transcription process. So that's what a promoter sequence is. It's just a place for the RNA polymerase to bind and initiate the transcription, the formation of DNA to RNA. The Kozak sequence, however, is again it's a DNA RNA sequence which surrounds the start codon that helps in ribosome translation. So, promoter sequence is considered when you're talking about forming an RNA from a DNA. However, uh, a Kozak sequence is considered when you're talking about initiating translation, which means forming RNA, forming a protein from an RNA molecule. So both of them are typically the same. Actually, the work is the same. They help in initiating the process, but what process we are initiating is different. So, if you're talking about a promoter sequence, it's initiating transcription, and if you're talking about a Kozak sequence, it's initiating translation. Okay, so this is the main difference. You don't have to remember this, but this is just something a part of. biochemistry that's going to help you. So you must know the difference between a promoter and a Kozak sequence. So the point mutation occurs in that in chromosome 11, which decreases beta globin synthesis, or it completely wipes out the beta globin synthesis. So either it could be a partial decrease, it could be a decrease, which means that which would be labeled by beta positive. So a decrease, only a decrease would be labeled as beta positive, right? And the complete absence would be labeled by beta naught. This is zero. So it's known as naught. So beta naught, right? Either it's going to be beta positive, which means beta positive does not mean that it is normal. You have to keep in mind that beta positive does not mean that it is normal. Okay. So for to tell you that beta positive is it does not mean that it is normal. Okay, you have to keep this in mind. Uh, they still mean that the defect is present, but uh, the defect is it's not wiping out the process completely. However, if it is completely absent, then it will be just written as beta naught. Okay, there is increased prevalence in the people of Mediterranean descent. You have to keep this in mind; it's very important as well. So, people from Mediterranean descent are at increased risk. Okay, keep that in mind. Now, because uh, there were four alpha chromosomes that coded for alpha uh, gene, right? As far as beta thalassemia is concerned, there are only two chromosomes. So there is not a lot of combination that could happen. There are just some combinations that can happen, and those combinations are given here. Important part here is to just remember the clinical outcome of every part. So you just need to keep in mind the clinical outcome of every part. So either you can have beta thalassemia minor. Beta thalassemia minor means that there is only partial disruption in the uh, you can say there's only partial disruption. So if one beta chain is normal and the other one has partial decrease, right? So this plus I told you guys already means that it's decrease. So it's going to be known as beta thalassemia minor, and which is going to give us microcytic anemia and nothing more. Okay. Beta thalassemia intermedia means that if none of the gene is normal, right? So you don't have a normal gene in intermedia. You have a normal gene in minor, but you don't have a normal gene over here. So there is no normal, right? So no normal. Okay. And one of the genes is either partially absent, or it's one of the genes is either completely absent, excuse me, or it is partially absent. But both of the genes are defected. Both are defected. One could be either completely absent or one could be partially absent. Okay. This is known as intermediate because this is in the middle. And it can cause variable anemia. It's asymptomatic. It can cause us to go on transfusions, but uh, it's not decided. Beta thalassemia major, on the other hand, is when both of the genes are affected. So this could be written as like beta naught. Both of the genes are absent. So or slash beta naught. So this is how they could write it. Just made it a bit dramatic. Let me tell you the simplified way. So this is how it could be written. Right. This is the this is the part where they could write. So beta thalassemia major is also mentioned as Cooley anemia. You have to remember this name. They might somehow ask this somewhere. They might mention this, and it is a severe microcytic anemia, and it has target cells, and it also has an isopoikilocytosis, which is just a fancy word for saying that there is a wide variety of shapes and sizes of RBCs that are existing in the blood. So they're not isometric. There are a wide variety. So there is either it could be a smaller RBC, there could be a large RBC, there could be an oval-shaped RBC. So there's a wide variety of RBCs present. That's what anisopoikilocytosis poikilocytosis means is that there is a variety of shapes and sizes of RBCs that are present, and it does require blood transfusions, which can lead to a secondary risk of increased risk of secondary hemochromatosis, which is acquired hemochromatosis. This is something that you need to keep in mind. What happens is that because RBCs are not, it's a qualitative defect. So the bone marrow tries to compensate it by expanding, and when it expands on the skull, it gives us a crew cut appearance on the skull accident, which is a skeletal deformity, obviously. So the reason why the crew cut appearance is occurring is due to extramedullary hematopoiesis. The hematopoiesis is not limited to the bone marrow in our bones. Now, what is happening is due to compensation of the decreased amount of RBCs in the blood, the bone marrow starts to uh, produce or carry out hematopoiesis in places other than just the bone marrow. It starts to create in places other than the bone marrow, so it on the skull or anywhere else. So, due to that, it can lead to hepatosplenomegaly because uh, liver and spleen are also reticular endothelial organs. So, they are going to increase. There is going to be extramedullary hematopoiesis. So, in those organs will are also going to carry out hematopoiesis as well. So that's the first part that you must be careful about, is that what is the reason behind the skeletal deformity is because hematopoiesis is going to be carried out in various other places other than just your bones. So I'll show you guys what it looks like. So if I could just show you, because this is an important image that you must be, I don't know what's this, but yes, this is a classical image. You can see that the crew cut appearance over here, where my cursor is. You can see that. So this is just a marrow that is deposited on the skull, and the reason why it's deposited on the skull is because it wants to carry out hematopoiesis. It thinks that somehow there is some defect in hematopoiesis, which there is. There is a defect, but it's a genetic defect, so it cannot be solved by increasing the bone marrow. These people are also an increased risk of a parvovirus B19 induced aplastic crisis. So, what a parvovirus B19 does is that it decreases hematopoiesis, right? So, if someone is already suffering from that kind of a problem, and if that person gets infected with this virus, then this could make things go a lot worse. So, those people are particularly at risk of getting an aplastic crisis. Aplastic crisis just means that there are no RBCs present. So there are no RBCs in the body. Parvovirus B19 basically shuts down the RBC production or hematopoiesis. So if it is happening in a person who is healthy, it wouldn't really cause much effect, because the person can already has a sufficient amount of RBCs in the blood to carry out the function. But for someone who is already deficient in RBCs, this virus could be lethal for that person. I think the most important part is this part. This is what is usually given in the question, that HBF and HbA2 are going to be increased. So you need to keep this in mind. It's very important, quite important. They've hidden it over here. So HBF and HbA2 are going to be increased. This is going to be a sign for you in the clinical question, that this they are talking about beta thalassemia. And the child usually becomes symptomatic after 6 months, because that's when the HbF declines. So if the HbF is already in the body, because the problem is with which normal adult hemoglobin, that's the problem in which the problem occurs in adult hemoglobin, right? So HbF is completely fine as long as it is there. HbF is protective. But if it starts to decrease as a newborn, it starts to decrease after 6 months of life, then the problem starts to arise when there is a need of adult hemoglobin. So that's when you have to go for transfusions after 6 months. So you have to keep this point in mind. Chronic hemolysis in beta thalassemia can lead to pigment stones as well, which is again an important point. So that's what beta thalassemia major can do to your body. These are important points for you to remember. And there can also be a combination where sickle cell gene could be combined with beta thalassemia. It could be sickle cell beta thalassemia. It is rare, but patients can get infected, or should I say, get affected by both of these problems at once. And this just causes a moderate sickle cell disease, depending on whether there is decreased beta thalassemia or there is absent beta thalassemia. It depends on the symptoms. So yeah, this is another possibility that you have to keep in mind. Okay. All right. So lead poisoning. So lead inhibits phenyl and ALA dehydratase, and these are the two enzymes that are important in your heme synthesis. So they decrease heme synthesis and they increase RBC protoporphyrin. The reason why they increase RBC protoporphyrin is because protoporphyrin is needed in heme synthesis. So if heme synthesis is stopped, protoporphyrin starts to accumulate and it decreases in the blood. It also inhibits rRNA degradation. So what it does is that the RBCs retain aggregates of rRNA, so it causes basophilic stiffening. So that is the reason why basophilic stiffening occurs. I've also explained this in my previous video. Because RNA fragments are basophilic, and when they remain in the RBCs, they can cause a specific appearance of a dotted appearance, basophilic dotted appearance. There is a mnemonic given that you can remember, which is known as lead in itself. And this shows us the clinical presentation of the patient. It can present as lead lines on the gingiva, which are known as Burton's lines, and on metaphysis of long bones. So this is the Burton line, as you can see. This is the Burton line. There is the arrow. It can be visualized by this as well. They're not just they don't expect you to just recognize it by the picture, so they're also going to give us a clinical case. But you have to know. So lead lines on the gingiva, I think we are able we could see them. So this is the line. You can see these are the Burton lines. Okay. And encephalopathy can occur, basophilic stippling can occur, abdominal colic, quite important. This is a very common sign. They give this in the question, and pseudoblastic anemia first can occur. Pseudoblastic anemia, very important. Again, an important sign, drops. So wrist and foot drop can occur, and this is a neurological sign. So most students get distracted thinking of a neurological disorder, but this is important. Abdominal colic is also quite important. They could mention constipation as well. It's very important. And decrease in the mental capacity, encephalopathy, causing confusion and related symptoms. Treatment is with Succimer, EDTA, and dimercaprol. You have to remember all three are quite important. They are all three quite important. So a particular point that you must remember is that the exposure is increased in old houses built before 1978 with chipped paint and the workplace. So they don't usually mention the chipped paint nowadays. They don't mention that because it's been quite used quite a lot, but they can mention workplace as adults. So they could mention these possible symptoms. Uh, they are commonly appearing in an adult, and they could mention that he is working in an old office. So that's how you could get an idea that this is a lead poisoning question. But for to take away something, just take away the clinical feature is quite important. Pseudoblastic anemia is the same as basically lead poisoning. It's basically lead poisoning is the cause of pseudoblastic anemia. But what pseudoblastic anemia is basically is that it could be a genetic cause in the ALA synthesis gene, or it could occur in a myelodysplastic syndrome. Alcohol is the most common reversible cause. So this is an important point that alcohol is the most common cause of sideroblastic anemia, the most common uh, reversible cause. Reversible causes also include lead poisoning that we studied just before, vitamin B6 deficiency, very important, and copper deficiency, and isoniazid is already also causes. So I would suggest that you keep in mind all of these reversible causes. These are quite important. So alcohol, lead poisoning, vitamin B6 deficiency, copper deficiency, isoniazid, linezolid, all of these are quite important. You have to keep this in mind. Lab findings, we discussed them before also, but of course, because it is a macrocytic anemia, so it's going to have a decrease in MCV, but it is not the deficiency. It's not due to a deficiency in iron. So iron is going to be increased because it's not being used, right? ALS synthase is affected, which means heme synthesis again is not occurring. So iron is getting accumulated. Iron will also get accumulated in this as well. This, however, affects different enzymes. I've mentioned over here fucoridase, ALD hydratase, iron degradation. This affects ALS synthesis. So you have to keep in mind the enzyme that both of them affect, right? Don't get confused in both of these disorders. These are different disorders. Just that the lead poisoning is a cause of sideroblastic anemia. So iron is going to accumulate, PIBC is going to decrease, ferritin is going to increase, and it's going to lead to formation of ringed sideroblasts, which basically I've also explained that this is an RBC, and the iron starts to deposit in a circle. So that's why this is known as a ringed sideroblast. If you're going to stain it with Prussian blue, it's uh, it's going to visualize the iron deposition for you. So after staining the Prussian blue, using the Prussian blue stain, you can see the deposited iron in a circle in the bone marrow. You have to keep that in mind. You have to. This is seen in the bone marrow. So in the bone marrow, peripheral blood smear, peripherally, it's going to show you the basophilic stiffening of RBCs. Now, what is the difference between a bone marrow stain and a peripheral stain? I have, and what is the rationale behind it? I have explained in a previous video. You can see that, but this is a difference. You must know that ring sideroblasts are always seen in bone marrow most of the times, and peripherally, it's just the basophilic stippling of the RBCs. Yeah, so some variants may be normocytic or macrocytic, but this is very, very rare, so you don't need to remember this part. The treatment is with pyridoxine B6, and which is a cofactor for ALA synthase.